Okay, so today we are going to introduce I rules. These are farther logical rules. Um, so S rules were rules that you could use with one statement of a particular kind. For every kind of statement that you do not have an S rule for, I will give you an I rule for. But an I rule requires not just one statement, but a combination of two statements that work together in a particular way. So that is the main distinction between S rules and I rules. Upcoming schedule, Friday. Again, Friday I can't be here, so I'm going to provide a video link not to a video call, but to a video that reviewing some highlights of S rules and I rules. Monday will be our in-class review, and then Friday is exam, I'm sorry, no, not Friday. A week from today, on Wednesday, is exam 3. So Friday is a video link and an exercise. Next Monday is our in-class review. Next Wednesday is exam 3 held here. Bring your device, we'll take it online. Questions about logistics, about upcoming stuff? Yes, ma'am. Yes, this will include the inductive reasoning and the probability. You are allowed to bring a calculator. I do find that this makes people overconfident. So you're allowed to bring a calculator, but honestly, I don't think it'll help you that much. Because people assume the calculator will make it easy. And really the hard part is knowing how to set up the problem, not doing the math, you know, the eighth, ninth grade level math that most of us would just do out by hand on paper. So, yes. I am trying to set up a student, the student tutor to do a review session, but there will definitely be an in-class session on Monday. Yeah, so either look for an announcement about that. All right. So let's get these I rules. All right, let's get these I rules going. So as I said, I rules are general rules of inference that are drawn from specific combinations of two claims. So I told you last time that I gave you an easy S rule for AND. The S rule for AND is real intuitive. If you have a regular AND, which says both A and B are true, then you can infer out both halves. If both A and B are true, then A is true. And also B is true. Shocking, easy stuff. You didn't need a logic class to know that. But here's something a little less intuitive. This is called conjunctive syllogism, or the not both rule, or the not and rule. And it's from not both P and Q. So this is the rule to use with negated and. I gave you an S rule to use with regular and last time. Now we're going to do the rule for negated and. So from the combination negated and additionally the match of one of the two sides, you can infer out the opposite of the remaining side. So again, to say this in English, this says it can't be that both P and Q are true, and we also know that P is true. So if we can't have both of them true, but we know P is true, then we can infer the opposite of the remaining side, not Q. And it works with both sides. So you can also do, it's not the case of both P and Q, and then you can match Q. And once you do that, you get the opposite of the remaining side. You get not P. So again, you need two statements. You need the negated and statement, and you need a statement that matches exactly one of the two sides. And from that, you can get the opposite of the remaining side. All right, and let me add, this also works with negated statements inside. So let's say I have a negated, not both, not P and Q, and I can match one of the sides, not P, then I can still get not Q. So again, from not both, you need the combination of the not both, the not and and the exact match of one of the sides. And anytime you can do that, you can infer out the opposite of the remaining side. And if we had both sides negated on the and we have the match of one of the sides, we then get the opposite of the remaining side. So from not both, not P and not Q, not P, you would get the opposite of the remaining side, which is Q. Everyone see what I did there? Yes?
So you're never going to change the first letter, like with the Q, you change something to the sign.
Right.
Never do it with the first letter.
Well, I mean, we could do that. So I could take that negation off the P, and as long as I have the exact match of the P, then we would get the opposite of the remaining one. Right. I mean, you know, again, it works with this one too. So let's say I add a negation to the Q. So not both true positive P and negative Q. We match the negative Q. We get the opposite of the remaining side, which is P gets switched to not P. So again, the only thing that can never change is you need that negation outside. In my opinion, this is probably the hardest one. So we're starting with the hard one first. All right. Let's continue. All right, so that's called conjunctive syllogism, or you can call it just the not and, NAND, or not both rule. Any of those, the lingo for any of those would work. The next one is the or rule, sometimes called in the Latin disjunctive syllogism. And this is where we have an or, and we have the opposite of one of the two sides. This is where we have P or Q, but not P, therefore we have Q. Or to say it somewhat differently, let's say I offer you, and I ask, would you like peanut butter or jelly? Or actually, let me be a little more authoritative. Let's say I'm your dad, and I say you have to have either peanut butter or jelly. And you say, but I hate peanut butter. Well, guess what? We will predict what the result will be. You will have jelly. And again, it works with either half. So from P or Q, not Q, you would get P. So you need an or statement with no negation outside. The negation changes everything. So you need an or statement with no negation outside. You need the opposite of one of the two constituent halves, and then you infer out the remaining half. Sometimes I do the or rule like this. I negate one of the halves. So if I see P or Q, and I see not P, I will cross out, I will sort of do something to indicate that the not P cancels the P, and therefore we're left with Q. And of course, it works with negations as well. So if I have either P or not Q, and I have the opposite of not Q, which is Q, I can still infer out P. But matching one of the halves doesn't help. So if the not and, matching one of the halves is what you need. For the regular or, the opposite of one of the halves is what you need. So whenever you see an operator, whether it's an and, an or, a negated and, a negated or, you want to ask yourself, what is the rule for this? And if it's an I rule, you need to ask, what is it that I need to combine this with to make the I rule work? For negated and, you need a match of one of the halves. For regular or, you need the opposite of one of the halves. I mean, it's not rocket science. but it is a lot to keep track of conceptually. All right, now for conditional arrow. And I'm actually going to give you two separate rules for arrow. Arrow is the only one that gets two rules. And this is the first of them. And the first one, I think, is pretty intuitive. Remember, conditional says, if the left side is true, then the right side must also be true. So if the left side says, if you have a P, then Q must also be true. So we also match the left side, P, and we get out Q. So remember, conditionals are sometimes called if-then. So whenever we fill the left side, we match the if. And if we can match the if, we then get the then. So, but you have to have an exact match. There can't be a negation outside, and it can't be the opposite of the left side. It has to be an exact match of the left side. So if you can match the left side, you get the match of the right side. Now, if you match the right side, that doesn't get you anything. You see, this arrow only goes in one direction. So a P guarantees a Q, but a Q does not guarantee a P. So you can only go left to right. All right, so that's one arrow rule. I sometimes call it left to right arrow rule. The technical name is modus ponens. Then we have the second arrow rule, which is sometimes called modus tollens. Again, we have the same first statement, if P then Q, but this time we're going to add the opposite of the right side. And from the combination if P then Q, the opposite of the right side, which is not Q, we can infer the opposite of the left side. And again, that works with anything on the right side that you can get the opposite of. So when you see an arrow statement, you've got two ways to use it. Remember, no negation, but a non-negated arrow statement. You either need to match the left side to get the right side, or you need the opposite of the right side to get the left side. Those are your two options. And matching the right side doesn't get you anything, and negating the left side doesn't get you anything. You have to either match the left or get the opposite of the right. The arrow can be tricky just because, you know, there's a lot of directions you can go in. All right, let's get some practice. Let me get our session number up there. All right, our session number is going to be 926009. All right, what, if anything, can we derive from the combination of negated W and T and the additional claim W? What, if anything, can we get from that? Can we get both not W and not T? Can we get T? Can we get not T? Can we get not W? Or can we get nothing? Good. So from not both W and T. Since we know we have W, we can't have T. So not T is correct, which 73% got. How about S or L and S? What, if anything, can you get from this? Okay, 57% are correct. Remember, with an or, matching one of the sides does not help. We need the opposite of one of the sides. So with the opposite of one of the sides, you can negate that side and infer out the remaining side. But from a match of one of the sides of an or, you get nothing. If H, then not B. And we also have H. Good. All right. That's nice. 100%. You all got it. So, right, from an arrow statement and then matching the left side, you get the match of the right side. Very good. How about this? If X, then E, E. Good. Right. Matching the right side doesn't help. You need the opposite of the right side. So you get nothing from this. The arrow only goes left to right. It can't go right to left. All right. From not B and S and not S, what can you get, if anything? All right. Now, from not both, you need to match one of the sides. Does S match one of the, does the not S match one of the sides? No, it does not. You need the exact match. So you have non-negated S here. You need a regular non-negated S here. This negation ruins it for you. Therefore, the proper answer was nothing, which only 40% got. So again, with the negated and, you need to match one of the sides. And if there's a negation inside the and statement, then you need a negation. But if it's plain inside the and statement, then adding the negation prevents it from working. If not Y, then K, and the extra claim Y. What, if anything, can you get from this? Right, the correct answer is nothing. The arrow statement says, if you have a not Y, then you can have K. So what we need to make this work is a not Y. But we don't have a not Y. We only have a Y. Therefore, you can get nothing, which is what 2/3 of you correctly identified. So again, it has to be an exact match. Either K or not R, and the additional claim R. What, if anything, can we get from that? All right, well, the program doesn't want to tell us. All right, so let's talk. So with the or, what are we looking for? We're looking for or plus what? Yeah, so we need the opposite of one of the halves. So we either need a not K, or we need a R. So we already have not R. The opposite of not R is R. So we have that. And that leaves us with K. So K was the correct answer. Not both, not S and W. And additionally, not W. What, if anything, can we get from this? Good. Right. So this is a not both. To make the not both work, you need to match one of the two sides. To match the W, you need a plain W, but we don't have plain affirmative W. Instead, we have negated W. And therefore, we get nothing. If U, then G. Good, easy. It's a basic arrow rule. You need to match the left. We can match the left, therefore we get the right. Very good. Either not I or K, and the additional claim K. All right, this is an or statement. To make the or statement work, we need the opposite of one of the sides. What is the opposite of K? Not K. Do we have a not K? We do not. Therefore, we can get nothing, as the 62% recognized. Either not N or not A. And additionally, A. All right, so we have not N or not A. We additionally have an A. To make the or statement work, we need, yes. I can try. Not N or not A. And additionally, A. That a little bit better? Good. All right, so what do we need with an or statement? We need the opposite of one of the halves. So we either need the opposite of not N, which would be N, or we need the opposite of not A, which would be A. So we have that. And we are left with not N. If not A, then not E. And the additional claim, not E. Good. That's right. Matching the right side doesn't get you anything. You need the opposite of the right side. Good. On the whole, you seem to be doing well with the arrow statements. You seem to be struggling with the other two kinds of statements, with the or and the and. But you seem to be doing okay with the arrows. Okay, not both, not F, and not Q. And the additional claim F. Turning Tech does not want to tell me what you think. All right, so here we have a negated and. Not F, and not Q. And the additional claim F. Now, negated and tells me both of these can't be the case. So to infer something, I need to match exactly one of the halves. But I cannot match one of the halves because I have the opposite of one of the halves. Therefore, I get nada. Nothing. Niche. Nicked. Yes, you need to match both the letter and the affirmative negative. Both of them have to be exactly the match. So because this is negated, I need a negated F to do the inference. And this does not match because one's a negative and one's a positive. This is the opposite. If I had an or, then I could do something. But negated and, I can't do anything. Yes. So yeah, so affirmative F and double negated F are actually the same thing. So right, so this is also a not F. That sounds right. So here, so remember, the not and means not both. So we need, so both of these can't be the case. So if we know one of these is the case, then the other one can't be. But F doesn't match this, so it doesn't help. But yes, it is, an affirmative and a double negation have the same logical value. If that helps you think of it that way, as it does him, if that doesn't help you, don't think about that. Don't think about pink elephants. All right. Not both A and not Y. All right, so we need to match, this is a negated and, we need to match one of the two halves, and we can match one of the two halves. So that gets us the opposite of the remaining half. So that gets us the opposite of not y, which is what 53% of y'all got. All right. So I doubled down on my earlier observation. With the arrow statements, you're mostly getting it. But for some reason, with the or, and especially with negated and, we're having some trouble. So let's talk about that. What is befuddling about the negated and?
I think my biggest thing is not factoring the negation from outside the parentheses and matching them to the inside.
Good, good. So yeah, so when we're looking for the match, we're not really, this just tells us we need to find an exact match. But after that, then we stop looking at that. So don't try to like distribute that negation to both halves. That will just confuse you. So once you recognize it's not and, then just focus on what's in the parentheses. And you need the exact match of one of the halves.
I think another thing is it's easy to remember like or is opposite, and then the and one and if you match them, but then you forget so you put opposite out of your mind, like now think about the opposite and then you can match them, and it's like but then it's the opposite of the other one.
Right, right. So you need to match and then do the opposite. And so yeah, I mean, look, ultimately we need to do practice. We need to memorize this. But yeah, part of it is it's not as intuitive where if you get the left side of the arrow, then you get the right side of the arrow. That sounds pretty straightforward. But matching one half to get the opposite of the other, that's a little less straightforward. You had your hand up. Okay, that's fair. All right. Let's make this a little more complicated. So, when you are doing logic, normally you are not told whether or not you are supposed to use an S or an I rule. The goal is for you to get to the point where you can look at the kind of operation the problem uses, whether it's an and, negated and, an or, a negated or, an arrow, or a negated arrow, and you can immediately recognize which rules are relevant and whether they are S or I rules. So when you combine them, sometimes I won't tell you whether you need to use an S or an I rule, which means you might just need to use a regular AND rule, which is an S rule, or you might need to use a negated AND rule, depending on whether I give you a regular AND or a negated AND. So here we go. Not both U and T, and the additional claim T. Good. So here we have negated and. Negated and tells us we need to match one of the halves, which we can, and that tells us to get the opposite of the remaining half. Very good, 73%. All right, we have negated, not B or C. What, if anything, can we do here? Okay. Yes, so this is an S rule because we have a negated or. They did kind of make it a little easy for you in that they didn't give you a second statement. So if you're going to do anything, it's got to be with an S rule. And the negated or gets you the opposite of both sides. And that switches the not B to B and the C to not C. If A, then not B. All right, from regular, if A, then not B, and nothing else, you can get nothing. Because you either need the match of the left or the opposite of the right. Now, if you have a negation out front, then you can get the match of the left and the opposite of the right, which would be A and B. But from this, you can't get anything at all. So again, there is a chart on one of your pages where it has all 6 or 7 of these rules in one place. If I were studying for this exam, I would photocopy that page, I would print it out. Actually, I print out like 5 copies, and I would just put it everywhere. And I would stare at these until I automatically knew which rule to use and how to use it. Because again, as I've been saying with other things, you want to get this down cold, because the final section completely depends on your ability to use these rules. So if you're already getting a third of them wrong with the way these rules work, then the final section will be impossible. So you want these down. You want them down cold. You also want to hasten that test. So another reason to want them down. Questions, thoughts, observations? You're allowed to say, this is hard. This is hard. Most people aren't good at logic. The truth table. So yeah, so the problem with the truth table is this. Because it's an affirmative rather than a negative, it gives you too many combinations. Too many combinations turn out to be true. So the truth table is helpful when only one combination is true. Where only one combination is true, that's where you can do an S rule. So here, let me do this for you. All right, so here, so you see the basic error rule, it's true in 3 situations. And because it's true in 3 different situations with 3 different combinations, you can't know what the value of A is and what the value of B is. But the reason why S rules work is because there's only one combination where the negated error would be true. So maybe this is easier if I just use an and. So A and B, there's only one out of the four combinations where A and B, the claim A and B is true. It's where A is true and B is true. And where you have other statements where there's only one combination of the values where the statement would be true, that's the conditions where you can do an S-fold. But where you've got too many possible combinations of values could still be true, then you can't do an S-fold because you don't know whether the A is true, whether you don't know whether the A is false, whether the B is true, or whether the A is true and the B is false. So again, all that to say, S rules work when you've got these sorts of situations where the statement will only be true with one of four possible combinations. All right, I'm going to do one more thing. I'm just going to introduce an idea. I'm going to throw you a life preserver. I'm not going to put this on exam 3, but this is something you need to know for after exam 3. So I want to show you just a glimpse. Going to blow your mind. So for each of the rules I've taught you, you can do it with a compound statement of any length, so long as you are working with the outermost operator. So here. So remember, basic AND rule, from the claim A and B are both true, we can imply A is true and also B is true. In the same way, from the claim that both, if A then B, if and only if, either not C or D, and if not E then F, we can get the truth of both halves. The if A then B, if and only if, either not C or D, and also if not E then F, that both constituent halves are true. Now I say that just to give you a glimpse ahead. This is why you need to get the basics down with these rules, because it's going to get a whole lot more complicated. We're going to go down the rabbit hole through the looking glass after exam 3. And we're going to be doing some really messed up stuff. So, so the extended inferences let you do these with statements of any complexity. Yes. I mean, it's simple, but it's, oh my God. So don't worry about this until a week from Friday after we get past exam 3. But just to be warned, we're going some hard places. So what we're doing now is still comparatively simple. So master the way those basic operations work. Master the S rules, master the I rules. I'm going to give you a video and maybe some exercises for Friday. You don't need to be here on Friday. On Monday, we'll have an in-class review. So be here on Monday. Test here on Wednesday. Good luck. If you have questions, don't be shy. Shoot me an email. Wednesday is exam 3, 1 week from today, 7 days. Thank you. Thank you for your efforts. You can do it. Thank you very much.